Right now, as you read this, there are thousands of SR-20 DET engines running across Japan, Australia, the United States, and Brazil, slowly building toward a catastrophic internal failure that their owners know absolutely nothing about. Not because the information does not exist, not because the engineering is mysterious or complex, but because Nissan buried it in technical service bulletins that never made it into a single owner's manual, and because the aftermarket industry built an empire worth hundreds of millions of dollars selling you replacement cylinder heads, rebuilt valve trains, and machine shop labor that you should never have needed in the first place. What I am about to tell you will make your mechanic uncomfortable. It will make cylinder head rebuilders nervous, and it will save you from throwing thousands of dollars into a failure that was entirely preventable from the moment you first turned the key. This engine, the SR-20 DET, is genuinely one of the greatest turbocharged four-cylinder engines ever engineered. Nissan's engineers in the late 1980s designed something that was elegant, compact, powerful, and extraordinarily tunable. The engine debuted in the S13 Silvia in 1989, and it carried through to the S15 in 1999. For a decade, it powered some of the most celebrated sports cars Japan ever produced. Enthusiasts adore it for good reason. It responds beautifully to boost, it revs freely, it makes power in a linear and addictive way, and it has a character that modern turbocharged engines simply cannot replicate. But inside that beautiful cylinder head, Nissan made a series of compromised engineering choices that created a mechanical time bomb. And the clock on that bomb accelerates dramatically the moment you start chasing power, pushing the rev limiter, or running the engine hard on a track. To understand exactly what goes wrong, you have to go inside the cylinder head and look at the valve train geometry with real precision. The SR-20 DET uses a dual overhead camshaft configuration with a very specific type of valve actuation mechanism. Rather than using solid bucket tappets that sit directly over the valve stem or a simple rocker arm that pivots on a fixed shaft, Nissan engineers chose a floating Y-shaped rocker arm system. This design choice was made to reduce component count, simplify manufacturing, and allow hydraulic lash adjustment to function without requiring periodic manual valve clearance checks. It was, on paper, a clever and service-friendly solution. In the real world, under high RPM stress, it becomes one of the most fragile valve train architectures ever mass-produced in a performance engine. Here is what actually happens inside that head. When you push this engine above 6,000 revolutions per minute, the Y-shaped rocker arm sits between the camshaft lobe and the valve stem, and it pivots on a hydraulic lash adjuster, which is a small cylindrical component filled with pressurized oil. The hydraulic lash adjuster, referred to by engineers as the HLA, uses oil pressure to maintain zero valve clearance automatically. The design relies on a constant, stable supply of pressurized, clean, unaerated oil. That is the critical dependency. That is where everything begins to unravel. When an engine accelerates rapidly toward high RPM, the oil inside the sump begins to move violently. Oil surge, windage from rotating components, and the sheer velocity of the crankshaft churning through the oil bath all introduce air into the lubricant. This phenomenon is called oil aeration, and it is not unique to the SR-20 DET. Every high-performance engine deals with it to some degree. But in most performance engines, the valve train was designed with that aeration in mind, using solid components or shimmed buckets that do not depend on hydraulic oil pressure to maintain their geometry. The SR-20 DET's HLA system does depend on it, completely and unconditionally. The moment aerated foamy oil reaches the hydraulic lash adjuster, that adjuster loses its ability to maintain the precise preload that holds the rocker arm in place. The HLA compresses under the pressure of the camshaft lobe, and the rocker arm geometry collapses. The valve opens at the wrong moment, closes imprecisely, and begins to behave in a way that the camshaft profile was never designed to accommodate. Now, add the problem of valve float, and you have the second half of this catastrophe. Valve float occurs when the valve spring cannot return the valve to its closed position fast enough to match the speed of the camshaft lobe. At high RPM, the camshaft rotates so quickly that the spring, already under load, cannot generate sufficient closing force before the lobe comes around again. The valve bounces. It floats. it does not fully close. In a well-designed valve train, valve float is managed through spring rate selection, retainer mass reduction, and titanium components that minimize the weight of the reciprocating assembly. In the SR20DET, the Y-shaped rocker arm is a heavy, complex component. It has significant mass. Under float conditions, that mass becomes a problem that behaves according to simple Newtonian physics. Force equals mass multiplied by acceleration. When the camshaft lobe strikes that heavy rocker arm while the valve is mid-float, the impact load transmitted through the system is enormous. The rocker arm does not gently follow the cam profile. It gets struck, it flexes, and it begins to migrate laterally. This is where the shim ejection event occurs. And this is the detail that Nissan never wanted in the mainstream conversation. On top of each valve stem, there is a small hardened shim that sits between the valve tip and a retaining collar. In a stable, properly functioning valve train, these shims sit perfectly still, but when the rocker arm begins to move laterally due to float-induced instability and compromised HLA support, it strikes the shim at an angle rather than squarely. Physics takes over immediately. The shim, which is small and has very little mass retention holding it in place, ejects. It launches out of its seat with significant velocity, and it travels into the cylinder head in an unpredictable direction. If you are lucky, it lodges somewhere and you have a valve that no longer opens and closes correctly. If you are not lucky, that shim goes into the timing chain cavity, jams a chain guide, or gets ingested somewhere that causes secondary and tertiary damage worth thousands of dollars in parts alone before you even count labor. Nissan's engineers knew about this failure mode. Internal documents and technical service bulletins from the early 1990s reference valve train stability concerns in high RPM operation. But instead of redesigning the rocker arm geometry, reducing the component mass, or specifying a revised HLA with greater oil pressure tolerance, the solution was kept at the level of factory service documentation. The standard SR20DET, as it left the factory, was tuned to produce approximately 200 horsepower at an RPM ceiling that the valve train could tolerate. The problem does not announce itself at those parameters. It waits. It waits until the owner raises the boost pressure, fits an aftermarket camshaft with more aggressive lift and duration, removes the factory rev limiter, or pushes the engine hard on a circuit. Then the failure arrives without warning, often within seconds of crossing the threshold where the valve train geometry can no longer maintain integrity. The aftermarket industry's response to this failure has been exactly what you would expect from an industry that profits from repeated repairs. Machine shops rebuilt cylinder heads. Parts suppliers sold replacement rocker arms. Engine builders charged for complete valve train rebuilds. And the knowledge of why this was happening in the first place, and more importantly, how to prevent it permanently for a fraction of the cost, circulated only in narrow circles of experienced SR20 DET tuners who had learned the hard way. That knowledge did not get marketed aggressively. It did not appear in glossy magazine features or sponsored YouTube videos. Because there is no profit model in telling someone how to prevent a failure before it happens, the preventative solution is not complicated, and it does not require exotic materials or specialized engineering tools. It requires understanding two specific modifications that address the root cause of the failure at the mechanical level. The first is the rocker arm stopper, commonly referred to in the SR20 community as the RAS. This is a small bracket assembly that installs directly onto the cylinder head and physically limits the lateral movement of the Y-shaped rocker arms. By preventing the rocker arms from migrating sideways during high RPM valve float events, the RAS eliminates the angular contact between the rocker tip and the valve shim. It does not prevent float from occurring at the camshaft level. It removes the consequence of that float by keeping the rocker arm geometry aligned, regardless of what the camshaft and spring are doing above the rev threshold. Quality rocker arm stoppers are manufactured from billet, aluminum, or steel, and they install using existing cylinder head bolt locations or dedicated machined positions, depending on the specific version you source. The installation requires removing the cam cover, cleaning the mating surfaces, and torquing the RAS brackets to specification. If you are doing this yourself, you need a torque wrench, a clean workspace, new cam cover gaskets, and patience. The actual fitment time for someone who has done it once is under 2 hours. For a first-time installation, budget 3 to 4 hours, and follow a model-specific guide from a reputable technical source. The second modification is the dual guide shim conversion, and this addresses the shim retention problem directly at the valve stem interface. Standard SR20DET shims sit in a single guide retainer that offers minimal lateral constraint. The dual guide shim system uses a revised retainer geometry that captures the shim on multiple faces, dramatically increasing its resistance to ejection, even if the rocker arm contact becomes momentarily imprecise. This conversion requires removing the camshafts, replacing the retainers, and fitting the revised shims. It is more involved than the RAS installation, and it represents a complete valve train refresh at the same time, so it is logical to combine it with a high-quality valve spring upgrade that raises the float threshold and reduces the window of instability that initiates the failure sequence in the first place. Regarding oil management, the HLA aeration problem has a practical mitigation strategy that costs almost nothing. Ensuring that your oil level is maintained precisely within specification, not overfilled and not underfilled, reduces the windage effect that introduces air into the system. Using a quality full synthetic oil with low foaming tendency in the correct viscosity for your operating temperatures directly improves HLA stability. Some experienced SR20DET builders go further and fit a baffled sump or an AccuSump accumulator to maintain oil pressure during lateral acceleration events on circuit. These are track-level solutions, but even the basic practice of consistent oil monitoring makes a measurable difference in HLA behavior at high RPM. The community around the SR20DET has been doing this work for decades, and the depth of real-world knowledge held by experienced builders and long-term owners is extraordinary. If you are serious about understanding this engine at the level it deserves, the KURO Cars community is one of the most technically rigorous and genuinely helpful groups currently active around Nissan performance platforms. These are people who have torn down hundreds of SR20DET cylinder heads, who have documented failure modes with photographic evidence, and who share information because they love the platform, not because they are selling you something. Find them, engage with their documented build threads, and cross-reference their field data against your own engine's history and current state. What happened to the SR20DET is not an accident. It is a case study in how a known engineering vulnerability can persist for decades inside a beloved platform when the financial incentives align against disclosure and toward repeated repair revenue. The valve train geometry was never revised for the production engine. The HLA dependence was never addressed with a service bulletin that recommended preventative modification. The rocker arm stopper was never offered as a factory option or even mentioned in dealer service documentation in any meaningful way. Instead, engine builders got rich, machine shops stayed busy, and owners kept absorbing costs that should never have been theirs to bear. You now understand exactly what happens inside that cylinder head at high RPM. You understand the physics of valve float, the mechanics of oil aeration, and the precise sequence of events that leads from a perfectly functional engine to a pile of destroyed internal components in the span of a single hard acceleration run. You understand that the solution has always existed, that it is cheap, that it is permanent, and that the industry never wanted you to find it. Share this with every SR20DET owner you know, because the failure is silent until it is catastrophic, and the repair bill will arrive before the warning does. And if you think the SR20DET story is shocking, wait until the next video, where I walk you through exactly how Toyota's infamous 2JZGTE wastegate actuator was deliberately underspecified at the factory, creating a boost creep failure mode that has destroyed hundreds of thousands of dollars in turbocharger hardware across the world, and why the internal engineering review that identified the problem in 1995 was quietly shelved, because the replacement turbocharger market was simply too profitable to fix.